Yes, sir. Audible.
Okay, fine. So we will wait for a couple of more minutes, maybe 1 or 2 minutes, then we can start. So, okay, let me share my screen. So, screen is visible to you, right? Someone can respond.
Yes, sir. Visible.
Okay, fine. So, in last interaction session, we discussed practice assignment 2 and 3. So, do you have any doubt in that? So, no one is responding. This means that no one have any doubt. So, in this interaction session, let me discuss assignment practice assignment 4 and practice assignment 5. Then we will see some other things. Okay. So let's start. So here is the first question. So are you guys familiar with the definition of Noetherian ring? Please respond. Keep yourself unmuted. Since there are only 3 or 4 participants, you can unmute yourself always. There is no issue like. Do you know definition of a Noetherian ring? Muthu Kumar, do you know definition of Noetherian ring?
Every ideal is finitely generated.
Yes. Please respond. And there are equivalent 2-3 definitions. So the first definition, you can assume that these are all equivalent criteria. Every ideal should be finitely generated. Ascending chain of ideals should be terminate at finite stage, and every collection of such have a such if you take collection of ideas like, then it should have a maximal element. These all equivalent you can prove. So so we have to prove here that which of the following links are Noetherian. So first question. So okay. Which of which of the following links are Noetherian? So part, okay, first one is this. J, ring of integers. Okay, so tell me, is this Noetherian ring or not? Tell me. Vaishnavi, is this Noetherian ring or not? Ring of integers.
Yes, sir.
Why? Why?
Because every idea is principally.
Okay, you are claiming that. Okay, you are claiming that in a ring of integers, every ideal is principal ideal. So how you will prove that? Vaishnavi, how you will prove that?
Uh,
Okay. So what is the last one? Damas Magani. Okay. Whatever the name, Damas. Can you say how we will prove this?
Yeah, yeah, I'm trying to think about this.
Okay. No problem. So
Yeah.
okay. Claim. We are claiming that someone claim, Vaishnavi claim, I guess, in Z ring of integers, every ideal is principal. Ideal is principal ideal. Principal ideal. Okay. So we have to prove this one, right? So how we will prove? Okay. Okay. Oh, battery. Not working. Why this is not working? Wait a minute. Okay, how we will prove this? Tell me. Suppose I is an ideal. I is ideal. I is an ideal in Z. Now we have to say it is principal. So what property of integer we can use to say it is principal? What is the nice property integer does it? Which does not make sense in other rings, right? Like ring of real numbers, it does not make sense to say. Like in real number is filled, so obviously every ideal is a principal ideal, you can say there, because either it is zero ideal or it is whole of the ring. So that is not right. Only zero ideal is possible. So tell me, what is the nice property of integer we can use here so that we can show it is a principal ideal, any ideal?
Smallest positive integer in I.
Yeah, that is the property that makes sense here. If so, how we will say that a smallest positive, any ideal we can choose, and how we can say that it have a smallest positive integer? Can someone justify?
Sir, if there is some other element in the ideal, then it should be the multiple of the
Okay,
small.
that is fine. But how you will claim that there is at least one positive element? Why there cannot be all negative elements?
If it is negative also, then negative of that element will be there.
Okay, that I want to listen. Yeah, because it is additive subgroup. If there is a negative element, then its inverse, additive inverse also there. So positive element is there. So
Yes.
we claim that we prove that I have at least one positive element. So since I have at least one positive element, let D be the smallest positive integer which is in I. Then we claim I is equals to ideal generated by D, means dz. So how we will claim that? Suppose there is an element B belongs to dz, B belongs to I. Okay, let B belongs to I. How you will claim that it is some multiple of D? How we will claim this? So we want to show B belongs to dz, i.e. b is equals to dx for some x in z. So how we will claim this? Tell me what we can do here.
Use the division algorithm.
Okay, great. So b belongs to dz. So where I can use the division algorithm? Tell me. We can use division algorithm for b and d, right? So there exists by division algorithm b is equals to dq plus r for q comma r belongs to z and r less than r strictly less than strictly less than d. It should be, we can choose it natural number, right? Okay, sorry, ring it is right. Okay, so now what we can do? Now b is in I. My this element, what b is in sorry, what we have to show, this b belongs to dz. We have to b belongs to dz. We have to show. So we just want to show this r is 0. How we will show this? See, if r is non-zero, then r is already less than d. So we are getting something contradiction. So can you say someone? Can someone say to me? If r is non-zero, then we are getting some contradiction. Can someone say to me, please? Please unmute yourself.
So then B minus DQ will be in the ideal.
B minus DQ
will be in the ideal.
okay, B is in I and B is in I, so B minus DQ is in I, right? Then what?
Yeah.
Yeah. This implies
because,
R is in I. So what?
Because we have chosen D to be the smallest positive integer, which should be done.
Okay.
Because
since R is less than D, by this division algorithm, R is less than D and R is in I.
When you use division algorithm, right? 0 less than or equal to or less than.
Yeah, you can write. Okay, sorry. Yeah, we have this. You can write like R is strictly less than 3 and 0 is, yeah, fine. So R belongs to I. So this means what you can conclude from here? R is in I and R is strictly less than D. But we assume that D is the smallest positive integer. R is also positive but less than D. So this is a contradiction to our assumption. So this is a contradiction to our initial hypothesis, initial assumption that, okay, this is not contradiction. R can be 0, right? We should not write it as a contradiction. Correct. We should not write it as a contradiction, but this implies that R is 0. This actually implies that R is 0. Okay. This implies R is equals to 0. This implies B belongs to dz. So we prove that this implies I is equals to dzij precisely. So we are done. We proved that ring of integer is a principal ideal domain. That means every ideal is a principal ideal. So in particular, we have to prove that this is a Noetherian ring. But for definition of a Noetherian ring, every ideal should be finitely generated. We prove that every ideal is principal ideal, so generated by single element. So hence the ring of integer, it is.
Excuse me.
Yeah, tell me.
If r greater than 0, we get a contradiction. Therefore, r must be 0.
Yeah, that is fine, right? We write that R should be either greater than or equals 0 and less than D. That means we claim and we prove that R is in I. So if R is in, not be anything other than that, right?
How can you conclude r equal to 0?
Because D is the smallest element we assume. Sorry, yeah. Because D is the smallest in this ideal I we assume, and R is less than D. But R is also greater than equals 0. That only possibility is 0 because R cannot be 1 because 1 is a positive integer, but we claim that D is the smallest, right?
Now D is the smallest positive integer.
Yeah. So,
So if R equal
R cannot be positive integer, right? Like cannot be positive integer, right? Because D is the smallest one. So R has only possibility that it can be 0 only. Agreed or not?
the
Someone can.
explanation what you have written is not convincing.
Okay. So where you not convinced, right? B is in I, D and D is in I. So that means DQ is in I and B is in I. So B minus DQ is in I. So that means R is in I. So R is in I and D is smallest positive integer in I. Also R is positive integer. R positive or 0. But R is strictly less than D. So R cannot be positive. So only possibility for R is 0. So where it is not clear to you? Tell me, explicitly tell me where it is not clear.
No. It's okay. R must be 0. Because what I want is if R is greater than 0, strictly less than D, we get a contradiction. Therefore,
R
must
cannot
be
be
0.
greater than 0 because D is the smallest positive integer. So how R can be 0? Because R is in I, right? You can write in that way also, but this is also fine that I want to justify.
R belongs to I means R can be 0 also.
Yeah. Because I obviously have 0, right? It is an additive subgroup.
Yeah, yeah.
Okay. So the second example is that Rx is Rx, where Rx denote the. Okay, let me write here. Rx, where R is the field of real number. So tell me, is this ring Noetherian or not? Except Muthukumar, someone can unmute yourself and tell me, please, because he is responding, but no other one is. No, except him, no one is responding.
Yes, we are listening. You can continue, please.
Okay. So, okay. So we can someone respond that it is a Noetherian ring or not?
Not really yet.
Okay. So it is a Noetherian ring. Okay. We have to claim. So it is a Noetherian ring. We are saying this is a true. Okay. True. So how we will argue for this? Hilbert basis theorem.
First, can you explain this?
Yeah, I am explaining this, right? Hilbert basis theorem. Hilbert basis theorem. So what is Hilbert basis theorem? Do you know a statement of this theorem?
I have seen, but not exactly can remember.
Okay,
If you...
fine, no problem. So if R is a Noetherian ring, then Rx also Noetherian ring. Polynomial ring.
I am willing to know what is Noetherian ring.
Okay, wait a second. Rx is Noetherian ring. Okay, so there are some equivalent criteria for Noetherian ring. Let me do some whatever done in your course. So can someone tell me what definition? Because there, okay, let me write here definition for Noetherian. There are some equivalent criteria. A ring. So I guess you joined late in the class because I already did the definition of a Noetherian ring. So please join in time.
Yes. I got late it.
Okay. A ring R is said to be Noetherian if every ideal I of R is finitely generated. Equivalent to this, another criteria is that ascending chain of ideals ascending chain condition holds. This one you can write. Means ascending chain of ideas terminates at finite state.
Okay.
Okay, fine. So this is the definition. So
Yeah.
okay. So here is the, if we want to use this Hilbert basis theorem, it says that if R is a Noetherian ring, then polynomial ring over one variable with coefficient in R is also Noetherian ring. So since R is a field, so obviously it is a Noetherian ring because it has only 0 ideal. So it is a Noetherian ring. So Rx is a Noetherian ring by this argument, Hilbert basis theorem. This is a standard theorem. Its proof requires some standard tricks. I hope this is done in your course. It uses some standard trick called Rabinowitz trick. So maybe you guys interested in this, you should learn its proof at least once because the trick is useful. Okay. See, the third part is the ring of continuous functions from R. Okay, tell me.
Sorry, I wanted to ask about the this another equivalent definition of the ascending chain condition.
Yeah.
So
You can.
if
Collection of ideals should have maximal element, right?
Okay.
Yeah, there is third equivalent. Okay. The third part is that the ring of continuous function from R to R is this Noetherian ring. The ring of continuous function from R to R is this Noetherian ring. Unmute yourself and try to prove or disprove this. Otherwise, it will be a teaching session, not interaction session. So please unmute yourself. You can talk to me, discuss with me. Vaishnavi.
It is not Noetherian.
Okay, so wait a second. I will ask you, but let respond others also because they are not responding. So Vaishnavi, is this Noetherian ring or not? Okay, no problem. Okay.
Yeah, I think it is.
Yeah. So tell me what ascending chain I should take.
Okay. It's actually based on the fact that the R, we know the ideas in R, which are 0 and 1.
Okay.
Yeah.
So can you tell me clearly? Means your the audio is also not clear. So please be like, can you say some once again? Right, I cannot hear you properly. So can you say once again?
Sorry. I'm saying that because the ideas in R, the R is a field in here, so the ideas are 0 and 1.
Yeah.
So using the theorem that we have said, maybe in the Hilbert basis, we can have the conclusion.
So you are claiming this is a Noetherian ring?
Yeah.
Okay, so this is a Noetherian ring you are claiming. So any other one who is claiming that this is a Noetherian ring? Okay, Muthu Kumar, now your idea. What is your idea?
It is not Noetherian, which
So
has
what
been proved, which has been already proved in the video lecture.
Okay, so how you will prove me? How you will argue for this?
You have to construct a ascending chain which does not stabilize.
Okay, so what is the chain for that?
Yes, defined I suffix n.
Okay.
Set of all functions such that f of x equal to 0 for every x greater than or equal to n.
Okay, fine. That will form ideal. That is fine. And that, okay, yeah, that is a nice idea, right? So he gave some nice approach for this. Like you have to consider the ideal in such that it consists of polynomials f, f functions f from R to R such that okay, fx is equals to 0 for all x greater than equals n. So now see, what is I1? I1 consists of all function from R to R for which vanishes at all real number after n equals 1. Like this is my real line. Okay, this is my real line. So suppose here is 1. So this ideal consists of all functions which vanishes from here after this is on this whole of the line function vanishes. So fx is equals to 0 for all x greater than equals 1. Similarly, what I2? F such that fx is equals to 0 for all x greater than 2. So now tell me, what is the containment? So here is in, here is in plus 1, here is in minus 1. So
Yeah, I see.
so what side containment should I apply? In contained in in plus 1 or in plus 1 contained? So any element in I2, will it be also in I1 or any element of
Yeah,
I1?
yeah.
So what is
Every element in I2 is in I1.
okay?
So
Any
I2 contained in I1.
any element in I2 is also in I1, you are saying. So suppose give me a function. I am taking a function. This is my 1, this is my 2, and the function is this one. Except after this, whatever is here. So this is in I2 because it vanishes after 2, but this is not in I1 because it does not vanishes here, right?
Yeah.
So I give you an element of I2 which is not in I1.
Yeah.
So you are not correct, right?
N greater than or equal to 2 implies n greater than or equal to 1.
So Muthukumari, what do you want to say?
Okay, in is a subset of in plus 1. Okay.
In is a subset of in plus 1. I1 is a subset of I2. Yeah, because any function which vanishes greater than 1, that vanishes greater than 2 also, right? So yeah, this one should be continued. So in this way, you will get an infinite ascending chain. And you, as you can see strictly that this is a strict containment, like I1 is strictly contained in I2 because I give you a function that which belong to I2 but not in I1. Similar way you can argue like this is. So this is a standard proof, and Muthukumar is saying that this is done in your class. So this is the idea for this proof. So this is the idea, and you get an infinite ascending chain, even infinite descending chain. So this is neither Artinian nor Noetherian ring. So if you're familiar with Artinian ring. Okay, and D, last one is that the polynomial ring with integer coefficient in infinitely many ways. Okay, the polynomial ring ring Z infinitely many variables finitely many over Z. So tell me, is this true or not? The polynomial ring with integer coefficients in infinitely many variables. Tell me your inputs. Dharmendra Kumar, you can unmute yourself.
Jain sir.
Yeah, tell me.
Sir, assignment 5, graded assignment 5 is not given, in my side that cannot be shown. Non-graded assignment 5 is shown here, sir. So please, sir, clear about that.
Yeah, I am doing assignment 4 which is non-graded. Practice assignment.
Yes, what I have already done, but assignment 5 is a non-graded shown. Graded assignment 5 is not shown. So when assignment 5 is take over,
I could not understand you what you want to say. If you have any query, you can write to NPTEL.
assignment 5, sir, you are given assignment 5, non-graded assignment 5.
Yeah, I am not
Are you
TA,
very
I am not a instructor for this course. I am just a teaching associate for just a
Oh.
conducting help session for this course. So you can write NPTEL direct.
Oh yes, okay, sir.
Okay, fine.
Okay.
No problem. Okay, so someone is saying something, and so
Yeah,
how do
yeah. I was saying I claim that it is due to the Hilbert basis, since Z we have
okay,
already
so
shown.
tell me how you will use Hilbert basis theorem here. Tell me.
Yeah, our Z, the Z is already Noetherian.
So G is Noetherian, right?
Yeah.
So how you will argue for this infinite variable? In Hilbert basis said that ZX Noetherian. So now you can argue ZX Noetherian, then ZX1. Okay, let me write. Okay. So Hilbert basis theorem by Hilbert basis theorem. Since Z Noetherian, this implies ZX Noetherian, right? ZX1 Noetherian. Right. I am denoting variable x1. Now since ZX1 Noetherian, now since what ZX1 Noetherian, this implies ZX1, this is my ring, and taking it over variable x2. This is Noetherian.
Yeah.
By easy, but it is easy observation that this ring is same as Z x1 x2 polynomial ring into variable.
Yeah.
But how you will conclude for infinite variable? So give me your argument if you feel that still you are correct, because finite variable I give you idea that how you can conclude that polynomial ring in finite variable over a Noetherian ring is Noetherian. So but what about infinite variable?
Okay.
Okay, so if you have some ideal which is not finitely generated, then you are done, right? So try to think in that way, because for infinite case you cannot use this kind of assumption, because what is infinite minus 1? That is also infinite, right?
Yeah.
So this way does not make sense here. So try to think in some other way. Okay, someone want to answer this? This is almost obvious. You can just see in front of you what is the ideal which is not finitely generated. Just try to see the ring.
Yes, it is true.
Okay, so give me proof.
Proof.
Yeah.
प्रूफ के लिए
Okay, see, I'm not saying to you only, but I'm saying to whole class. In mathematics, is nothing without a proof and nothing without a counter example. So if you are claiming something, then you must have a proof. If you are saying that this is a wrong statement, you must have a counter example. Intuition doesn't matter until you have a proof, right? So it is fine that you are saying something, but I'm just saying that if you are saying something, you must have some idea about that how you are saying this. Otherwise, I can say yes or no. That is not a big deal for me. Otherwise, I can do this exercise in obvious way, true or false, and it will take 4 or 5 minutes.
I can think that it could. I can say that also by Hilbert theorem. X1 Noetherian है, X1 X2 है तो I could relate. But
I already explained you that idea where the problem comes arise in picture, because infinite minus 1 is also infinite. So you cannot proceed in this way, right? Someone is saying this argument, and I explain him why this is not the way. So think about some other way. Okay. Okay. Fine. So anyone want to give your inputs or should I give you solution?
You give.
Okay, fine. So let's take, we have to show, I am claiming that this is not an Eulerian ring. So I have to just give you an ideal which is not a finitely generated. So I am, or I have to give you ascending chain. Let me give you ascending chain. That is more easier or obvious that you can see easily. So I am saying that give you, okay, let me give you a chain. I am claiming the chain is this ideal generated by x1 contained in ideal generated by x1 comma x2 contained in ideal generated by x1 comma x2 comma x3 contained in this one. This is infinitely ascending chain because I have infinitely many variables, and this is a strict containment. So this is a non-Noetherian ring. Okay. So this is not a Noetherian ring. We are done. This this implies Z x1 x2 is not Noetherian ring. So okay, Damas, you agree with this?
Yeah, I agree.
Okay. So you found
Thank you.
problem. Where is in your idea? The problem is like you are saying you try to use Hilbert basis.
Yeah, it won't terminate.
Yeah. This is the problem there because infinite minus 1 is infinite. You
Yeah,
cannot use that.
thank you.
Okay, fine. So we will go to now second problem. This is done. So second problem. Choose all correct statements. So first one is that any integral domain is a field. Okay. So DS bias, can you say this is true or false? Correct or not?
Sir, I'll join in 2 minutes, sir. I'll join in 2.
Okay. Vaishnavi, can you say this is true or not?
Sir, it's correct, sir.
It is correct.
Yeah.
So give me a proof.
Uh, because it has no zero divisor and every element will be a unit. Unit.
Okay, how you will claim that every element is a unit?
Z is an integral domain which is not a
That
field.
is correct. So let me give him his point where he's thinking incorrectly. So how you will claim that every element is a unit? So every element, there is no zero divisor, right? So how you will claim that every element is a unit? You have some idea because I guess you are thinking about finite integral domains, but try to think about infinite case, because in finite case after some places you have repetition only. So that way you can argue that it is an integral domain. So it must have element must be unit, but here you cannot argue that. So this like you can think about infinite case. Then by using zero divisor property, no zero divisor property, you cannot say that this is this element is unit. So like the Muthukumar is giving you example. So take ring R is equals to Z, ring of integers. So you can see this is an integral domain, but can take element 2, which is not a unit. This implies not filled, but not filled. So the second option, second option is a finite integral domain is a field. Okay, now you are saying, I guess you are saying initially for this case, a finite integral domain is field. Okay. Damas, is this correct or not?
These statements, yeah, they are correct. The finite integral domain is a field. Yeah.
So, okay, how you will argue for this?
Yeah. Now we need to show that every element, non-zero element, will be inverted with the unit.
Okay, so how you will prove that? Suppose 0 is suppose a. Okay, let me write.
Yeah.
Let
Suppose A is non-zero.
0 does not equals to a belongs to R, where R is my integral domain. So we have to show this a is unit. So how you will argue? Tell me. Okay. Vaishnavi, I guess you tell initially that this is integral domain, finite integral domain is field. So how we will prove this? Muthukumar, do you have any idea?
A squared, A cube, A power 4, etc.
Okay, so what?
That cannot go infinitely.
Okay, so what?
So therefore, A power R must be equal to A power S.
A power R can be some element B. So how you can say that it must be A to the power S? How you will argue for that?
Without repetition, we will get infinite number of elements in that one.
Okay, I'm okay, fine. Yeah. A to the power R, yeah, that is correct. A to the power R should be A to the power S. Then what?
Okay, so maybe the R need to be less than S so that we can.
Okay, you can choose either
subtract.
R less than or S less than R. Then what?
Yeah.
Okay, let me write.
Yeah, and then we can
Okay,
subtract and try
yeah.
to.
0 does not equals to A belongs to R. This implies A square, A cube, so on. This is in R. All elements are in R. This implies that A to the power R equals to A to the power S for R does not equals to S. For some R does not equals to S, right? Agreed or not?
Yeah.
So this implies, suppose R less than S, because they are not same. So R less than S.
Yeah.
Then what you can argue? This implies A to the power R 1 minus A to the power S minus R.
S minus R, yeah.
It is 0. But R is an integral domain. So product is 0. That means one of the elements should be 0, right?
Yeah. So A power R will be equal to 0.
But A to the power R cannot be 0, right? Because A is non-zero element. We are in an integral domain. So it cannot have any nilpotent element. So this implies A to the power R, but A to the power R non-zero. So 1 minus A to the power S minus R must be equals to 0, right?
Yeah.
This implies A to the power S minus R is equals to 1. So that means, so how we will conclude from here? A is a unit. How you will argue? What is the inverse for A? For saying A is a unit, we have to find A inverse, right? What is A inverse here? A dot something should be 1, we have to prove. What is A inverse? Here is the candidate of A inverse. A to the power S minus R minus 1. Right?
Yeah.
So this is the A inverse. Okay. Now let me, where is eraser? This is fine, right? Muthukumar, this is fine, right?
How do you know the existence of one?
Existence of one means
Yeah, I think it's a
for me, definition of an integral domain is a commutative ring with unity without zero divisor. So what do you mean by existence of one?
Okay.
Okay. So the next problem is that any field is an integral domain. C part. Okay. So tell me, is this true or false? If true, then give me a proof. If false, then give me a counter example. Damas,
yeah.
how we will do this? Is this true or false?
It is true.
Okay, how will prove? Suppose
Yeah, so we need to assume that our ring is a field. So it means every non-zero element is
suppose
invertible.
okay, yeah. So you are claiming that any field is an integral domain. Suppose R is a field, you are claiming that it is integral domain. Suppose not, then what happens? You have to give some contradiction, right?
Okay. Yeah.
Yeah. Suppose not, then what happens? In a field, what is the property? Okay, let me write. Any field is an integral domain. Suppose it is not, then what? That means there must be some zero divisor. That means
Yeah.
this implies there must exist some zero divisor. Some zero divisor. So what is the meaning of this? There exists 0 does not equals to x.
Such that when you multiply, yes, is equal to 0 with
Such that
another element.
There exists 0 does not equals to x, and 0 does not equals to y, and
yeah,
but
the product equals 0.
Belongs to field is f, but x y is 0, right?
Yeah.
Yeah, but x and y are non-zero and both are element of field, so they are
Yes.
unit. So that means x inverse is there. So that means operate both side x inverse
Yeah.
dot x dot y is equals to 0. This implies y is equals to 0, which contradiction
Yeah,
because
yeah.
we assume that y is not. So this
Yeah.
is not possible. So this means this statement is true.
It's correct.
Yeah. Okay. What next part?
Sorry, sir. Maybe just to ask.
Okay.
Yeah. I was trying to think like if we maybe try to use the direct proof, what would be the problem then?
For what?
For such a statement?
For what theorem can you say again?
I mean, for this statement, like
Any field is an integral domain. So what do
if
you
you
want
use the direct proof, that assuming it is a field, then going to an integral domain, maybe.
Yeah,
Is it
this
that
is
we are
obvious statement. So how you will prove this? Okay, tell me. Yeah, there is some obvious proof also because yeah, tell me. Yeah, because it is almost obvious because field every element is unit, so cannot have zero divisor. Right? So, but how you will prove that? This seems to me most obvious. But if you have some more obvious than this, you can tell me.
Okay, I see. Okay, maybe I'll try to practice.
Okay, so the next one is, okay, dth one. If R is a finite ring, then R does not contain any non-zero nilpotent element. So is this true or false? If R is a finite ring, then R does not contain any non-zero nilpotent element. Is this true or false? Vaishnavi, is this true or false? Damas, is this true or false? Am I audible?
Yeah, yeah, you're audible. I'm trying to look at the. I'm trying to figure out from the these finite rings like the in Z, the Z mod NZ. So I'm trying to check this one.
Okay, you are thinking about finite ring, correct? So think about some. Okay, so Z
Yeah.
mod 2Z is a field, right? So in field there cannot be any nilpotent element. So you will not get anything. Z mod 3Z is also field. So think about Z mod 4Z.
Yeah, yeah. Yes.
Is there any nilpotent element?
Zero.
What is 2 bar square?
There's not, apart from the zero itself.
There is no nilpotent element in Z mod 4Z. What is 2 square?
Yeah. Two part is for to be zero. Yeah.
Yeah, so there is a nilpotent element, right?
Yes.
So we take R is equals to Z mod 4Z. 2 belongs to, matlab, you can write 2 bar belongs to R, but 2 bar square is equals to 0. So if R is a finite ring, then R does not contain any non-zero nilpotent element is false.
Yeah, sure.
Now next option. If R is an integral domain, and I contained in R is a proper ideal, then R mod I does not contain any zero divisor. Okay. So tell me, is this true or false? Muthukumar, is this true or false?
I think it is true
Okay, so give me a proof.
because R has no zero divisors.
I contained in R is a proper ideal, then R mod I does not contain any zero divisor. This is the statement. Like you have obvious counter example. Why you are saying this is true? You have some obvious counter example in ring of integer, right? Take R is equals to Z. If you are saying this is true, give me a proof.
So
Okay, tell me what you are saying something.
yeah, I was trying to consider the ring of integers that we said,
Okay.
which is an integral domain.
Okay.
And
What is the idea?
yeah, so I was trying to look at because the ideals are in the form nz, and
Okay. What is Z mod MZ, right? R mod I should be Z mod MZ.
yeah, it will be z mod nz. Yeah. So if n is equal to prime,
Then it does not contain any zero divisor.
it does
right?
not contain. Yeah.
But M need not be prime, right? M can be any composite number also.
Yeah.
So
So-
then it contains zero divisor, right?
Yeah, if it's a composite name.
Oh, yeah. So it is not true statement, right?
Yeah.
Agreed. Muthukumar, you are agree with this or not?
Yes, it is true.
The statement is false, right? This is not true.
Mhm.
Statement
R
is
is
false.
integral domain.
Yeah.
Need not imply R by I is an integral domain.
Yeah.
Zero divisor.
Yeah.
So, yeah. So let me write here justification, a small justification. Take R is equals to Z and I is equals to MZ, where M is any composite number,
Mhm.
then R mod I is equals to Z mod MZ contains zero divisor. Okay. So now next one, what is the next option? If R is an okay, this one we have done. If R is a field and I contained in R is a proper ideal, if R is a field and I contained in R is a proper ideal, then R mod I does not contain any zero divisor. Okay, so tell me, this is true or not? Damas, this is true or not? What's your
Yeah.
intuition?
Yeah, I'm thinking, sir.
So it's true.
Okay, so give me a proof.
Since it is a field, the only proper ideal or zero, because R has only two ideals. One is zero and whole R. So
R is ideal itself. Okay, so by definition you are assuming. Okay, so I guess in definition it should be given that it is not itself R. Okay, fine, you can assume that. Right. But okay, so let me ask you how much clear you in this book. Okay, so tell me how you will suppose I give you an ideal I and it is a non-zero ideal, then you are claiming that it should be whole of R. So how you will claim this? Vaishnavi.
one should belong to.
Okay, so how you will claim one is in that ideal? I'm saying this ideal is non-zero and you are claiming that one should be there. So how you will claim this?
Okay.
Tell me.
Okay.
This is almost obvious. I'm just asking because How much clear you are? I just want to see.
Yeah, you mean you're asking whether you're saying one is in the
Yeah,
ideal,
yeah.
right?
He
Yeah,
said
so
that
it means
any proper
yeah.
ideal is zero
Yeah.
ideal he is claiming. So I am just asking a proof for that. Like you take an ideal which is non-zero, you are claiming that it is whole of the R. So he claimed
Yeah.
that this is this contains one. So how I am claiming how you can claim that there is one in this side. So you can give me a justification for that. Damas, give me a
Yeah.
justification for that.
Yeah, to show that one is in the ID, it means the ID generates the whole of R.
Yeah. You understand question, right?
Yeah, that's that.
Okay. So it
Only
is almost
proper ideal in a field is zero ideal.
so okay. I am asking proof only for that. Because he said this statement, so I am just asking a proof for this because it is almost obvious statement.
A field
Suppose
contains only two ideals.
so how you will prove this? That is what I am asking, right?
You can take any ideal different from zero, then that ideal will coincide with R.
Okay, that's what I am asking for a proof.
Okay, you take an ideal which is
Yeah.
properly contains zero. That means there must be a non-zero element in I.
Right.
We are in a field, therefore inverse exists.
In field. Yeah,
Therefore,
right.
A inverse A belongs to I. That is identity belongs
Correct.
to I.
That is what
Therefore,
I want to hear from you. Okay, correct. Great. So in this way you can claim that any proper ideal is only zero ideal in the field. So now what is the argument, Vaishnavi, of your? You are saying this is true, right?
Yes, sir.
Yeah. Now what is your argument? Any proper ideal is zero ideal that we justify. So what is the further argument?
R mod zero will be R.
R mod zero will be R. How you? What is the isomorphism? R mod zero is just collection of cosets, right? You are giving a ring structure to that. So how you will claim this is isomorphism? Yeah, you are correct, but try to justify yourself, right?
Okay.
So try to justify what is the isomorphism. But because it is almost obvious always, and no book write this. But if you are not clear with this, then you always have a confusion in your mind. So try to be clear.
Okay.
Yeah. So what is the isomorphism? R mod zero, you are claiming that this is isomorphic to R. Yeah, you are saying something. Thomas, you are saying something.
Not yet.
So why it should be isomorphism? You should say something, right? It is almost obvious. Muthu Kumar, why R mod zero should be isomorphic to R?
A to A plus zero.
Yeah, that is the idea. Like this is almost obvious, but no one is justifying this one, right? No book justifies this, and you always think that this is obvious. But why it is obvious, you don't know what is the isomorphism. R mod I, which is zero element. So R, you are defining an isomorphism. Take an element A bar, which is A plus zero precisely. A plus zero. Send it to A. This is isomorphism. Just identity morphism, right? So this is isomorphism. You can check. So this is my isomorphism. Okay. So Vaishnavi, what is your argument after this? R mod I is isomorphic to R. So what? Vaishnavi, what is your argument after this?
Sir, it's a field, so all the elements will be a
Okay,
unique.
R is a field, so it does not contain any zero divisor. So that means R mod I also
R
does
mod.
not contain any zero divisor, right? So that is the correct statement. So this is the true statement. Okay, so we see that if R is an integral domain, then R mod I can contain some zero divisor. But if R is a field, then R mod I cannot contain any zero divisor, right? So this is the conclusion for this assignment. So let me open assignment 5 and we will solve that as means the practice assignment 5. Okay. This is the question. What happened? Let R be ring. Okay. So first option is if R is an integral domain, then any prime element in R is irreducible. This. Tell me. This is correct or not? You know definition of prime element or and irreducible element, right?
Yeah, that is it that it cannot be further factorized into some.
Okay. So tell me definition. Further factorized is not much clear from this word. So what is the definition? Tell me definition. What is a prime element? Give me definition. How you will say an element is a prime element in the ring R, integral domain? Okay. You don't know definition.
For me, I think it's a prime element in a ring. Or in an integral domain is an element in which it cannot be further decomposed into the product of other elements.
No, that's
That's
not.
my
Yeah,
intuition.
that is almost obvious. Like you are taking your intuition from ring of integer, but that is correct, but not exactly right. So this is kind of irreducible element decomposition, like irreducible decomposition. You are saying.
Yeah.
That is the definition of irreducible element. Somehow nearby, somewhat nearby. Right? But what is prime element? What is the a property of an integer in a property of a prime number in an integer? Suppose P divides the composite of two numbers, then what is?
P divides A or P divides B.
Yeah, that is the prime element. So is one is a prime element? Suppose one divides any number 3.4 equals to 12, right? One divides 12. Then is then one divides 3 and one divides 4. Is one is a prime element? I am just asking you in ring of integer. This is almost obvious because it is giving you intuition, right?
Yeah,
So tell me, is 1 is a prime number or not?
which is not.
Okay, so what how we can modify this definition? Vaishnavi gave a definition that P divides AB, then P divides A or P divides B. So how I can modify this definition? Because I gave you counter example, right? 1 is a not primary.
Okay. We have to take a non-zero and non-unit.
Yeah, that is the correct, because in ring of integer 1 and -1 are unit and 0 always divides any element. So we have to remove these elements, right? In any ring, we are saying a element P is a prime element if P is non-zero and non-unit and P divides AB, then either P divides A or P divides P. It is clear, right? Definition is clear. Should I need to write or it is clear? Damas,
Yeah, for me it is.
Muthukumar, the definition is clear or not? Okay. Vaishnavi, definition is clear, right?
Is a clear.
Okay. And what is the definition of an irreducible element? Tell me. Tell me definition of an irreducible element. I am waiting for your response. Damas,
Uh,
what is irreducible means? What you think about saying something is irreducible?
it is irreducible.
Yeah.
From a general intuition to me, it's like it cannot be decomposed.
Yeah, that cannot be decomposed. So now, take an analog of this in the case of ring, right?
Okay.
Tell me. Okay, let me write a definition here.
So
Okay. Vaishnavi, you want to add something? Okay. Definition I am writing here. Okay. So a non-zero, non-unit element in an integral domain, R, a non-zero non-unit element A in an integral domain R is irreducible if it does not have any proper divisor. Okay. So now what is proper divisor? The question is this. What is proper divisor? Damas, what definition you are giving in first case, that is almost same in this case, like what you are saying for prime element definition.
For the
Prime element definition, you are giving something like this, like I should write like A is set, what is the proper divisor means? B is a proper divisor of A. That means B divides A.
Yeah.
B is a proper divisor of A.
Okay.
Okay. B is a proper divisor of A if B is equals to
Yeah, is
sorry
equal
A
to
equals
a
to B.
multiple.
A equals to
Yeah, a
BC
multiple. Yeah.
for non-unit C and non-unit C for some non-unit C, and B is also
Okay.
non-unit. B is also non-unit.
Okay.
B does not equals to unit is proper divisor of A. If B divides A, B is a proper divisor of A, A equals to BC for B and C not units, right?
Okay.
If
Yeah.
B is a unit, then like if C is a unit, then B also A also divides B. Then A divides B and B divides C, right?
Yeah.
Yeah, in that case, because if C is a unit, you can take its inverse here, right?
Yeah. Yeah.
Yeah. So in that case, they are called associates. I hope this is done in your class. So in ring of integer, both like your intuition says, you give this definition for prime element. So in ring of integer, both these coincide. Like irreducible element is a prime element is a irreducible element. Like your intuition says that this should be definition for prime element because prime number holds this property also.
Yeah. Yeah.
Yeah, but in ring of integer, every prime element is irreducible, every irreducible element is a prime element. So that's why. But in general, it is not true. You will see some counter example, like in some non-UFDs, there can be some counter example, like some non-UFD. What is not UFD? Z root -3 or Z root -5, some like this. Yeah, there will be some counter example. Z root -5 or Z root -3, there will be some counter example. Yeah, Z root -3. Z root yeah, this is correct. There will be counter example. In particular, like Z root -5, you can take 2 and something like this. You will get some counter example. 2 and 6 or 2 and 1 plus root -5, something. Okay. Should I give you that example or you want to do me exercise? Tell me.
Yeah. Maybe you can give us the example.
Okay, fine. Okay, I will give you that example because, but in this exercise, we are doing something more than this. After this exercise, I will give you that example also, right?
Okay.
Agreed?
Okay. Yeah. Yeah.
I will give you an example of in this options. We will prove that every prime in an integral domain, every prime element is irreducible element. And after that, I will give you an example of a irreducible element which is not prime element, right?
Yeah.
Okay, that we will do.
Yeah. Thank you.
Okay. So now do this question first. If R is an integral domain, then any prime element in R is irreducible. How will do this? R integral domain hai, any prime element you can take and you have to show it is irreducible. And this is true statement. So let me give you a proof. How will prove this? Suppose P, we are saying that P is a prime element. Let
Yeah. Yeah.
P is a prime element.
Prime element.
Okay. So we have to show
That it is an irreducible.
Yeah, we have to show P is irreducible element, right?
Yeah.
How will show this? Suppose okay, right. Suppose for irreducible, what we have to show if P equals to BC, then either P like P equals to BC, then either B unit or C unit, right? This we have to show for it is like it is okay. What I am saying for irreducible, we have to show that P equals to like A equals to BC,
Yeah.
then either B unit or C unit, right? This we have to show. Otherwise, it has a proper divisor, right? If both are non-unit, then it has a proper divisor, right? Then B is a proper divisor of A in that. Agreed or not? If both B and C are non-units, then it have a proper divisor B or C for
Yeah.
A, right? So, so for irreducible element, it should not have any proper divisor, right?
Yeah.
So at least one of them should be unit, right?
Yeah, yeah, like in here when we have A is equal to B,
If both
C.
of yeah.
So
Right.
B and C, either B and C is the
Yeah.
is unit.
Yeah. So P is equals to BC. We have to show either B unit
Or C
or
unit.
C unit. Okay. This one we have to show. Now P equals to BC and P is a prime. So that means P divide BC, right?
Yeah.
But P
And,
is a prime. This implies P divides B or P divides C.
C, yeah.
P divides B. Okay, what I write? P divides B. P divides B. What this says? B is equals to
B is
P-
equal to the multiple of P. Yeah.
Px, right? And this
Yeah.
says C is equals to
C is
Py.
equal to P,
Py.
Py.
Right?
Yeah.
Now what you can do? Now P is equals to BC, right? Since P is equals to BC.
Yeah. Yeah. So we just multiply.
So if P is equals to B, if P divides B, then what we can say? If P divides P, P equals to BC, then we have this B equals to Px. This implies P is equals to Pxc.
Yeah. Yeah.
This implies P of 1 minus xc is 0, right?
Yes.
But since this is integral domain, it cannot have a 0 divisor. And P is a prime element, which cannot be 0. So that
Yeah.
means 1 minus xc should be 0.
Yeah. So
That means-
XC is equal to 1.
That means C is a unit, right?
Yeah.
Similarly, in other case, you get same conclusion, right? B is a unit in other case, right?
Yeah.
You can do that one, right? Should I do? Okay.
I will do that.
Okay, let me write here because no one is responding. If P divides C, this implies P is equals to
C is equal to Y. By.
P is equals to B Py, right? This implies P of 1 minus By is equals to 0. But since P is a prime element and this does not contain any 0 divisor, that means 1 minus By is equals to 0. That means B is a unit, right?
Yeah.
So we are done. So we proved that every prime element is, that means,
Reduce it.
so what we prove? So we prove P equals to, so if P equals to BC, then either B or is unit or C is unit, right?
Yeah.
That's what we prove. B is unit or C is unit. What this implies? P is irreducible. So we prove that every prime element is irreducible, right?
Yeah.
So we are done. This is true statement.
Okay.
Okay, let me give a counter example for converse. What is the, we have to give an example element which is irreducible but not prime, right?
Yeah.
Example of a ring R and an irreducible element such that A is not prime. Prime. Okay. We have to give such an example. Okay. So the obvious choice goes to, because in course you will prove that for unique factorization domain, this is equivalent statement. Like every irreducible element is a prime element and every prime element is a irreducible element. Over integral domain, we prove that every prime element is a irreducible element. So like we have to, and these definitions are defined for integral domains only. So we have to go for an integral domain which is not a unique factorization domain. So obvious choices comes for this kind of rings. So R is equals to, like you see in the ring of integer, every prime element is a irreducible element. So the obvious choices go for the ring R is equals to Z root minus 5. And what kind of ring? Like where you can make multiple of like Z root minus 3.
Hmm.
Do you know why I'm saying this kind of ring? Like here you have, let me give you an intuition. Like here you have 3.2 equals to 6. But see, this is same as 1 plus root minus 5 and 1 minus root minus 5. This factorization is not unique. Can you see, like 3.2 is also 6 and 1 plus root minus 5 and 1 minus root minus 5 is also 6. Can you see?
Yeah.
Yeah, so this is slightly, now you have to see the definition of unique factorization domain, but yeah, but this factorization is not unique. Similarly, in this ring you can see, like what is 4? 2.2 is 4, and
Yeah.
here you can write this as 1 plus root minus
Minus
3 and 1 plus root minus 7. Now you have a huge class of counter example, like you can see similar number of number, right?
Hmm.
Yeah. So now in this ring we have to find an element which is irreducible element but not prime. So can you give me? Like 2 divides 6, right?
Yeah.
3.2 equals to 6, and 3 is not unit and 2 is not unit. You can see. Okay. 3 is not unit, right? In this ring, 3 is not unit. Let me give. What is the unit in this ring Z root minus 5? Do you know? I hope you've done this exercise, right? I guess it should be like those norm 1 thing, right? A square plus 5b square should be 1. Only these elements are unit in these rings, right? So elements of the form like A is equals to, yeah, this is correct, right?
2 divides
Yeah, you are saying something?
2 divides 1 plus root of minus 5 into 1 minus root of minus 5.
Okay.
But 2 does not divide either of them.
Yeah, so what? So it is not prime, right? You want to say this thing. That is fine. But I am saying that what are units in the ring Z root minus 5? Okay. I hope you prove these exercises, like norm 1 can be only unit. Norm 1, like there is norm 1 like A square plus 5b square in these rings, Z root B kind of rings. Do you prove the what are the units in ring of Z iota?
Z I.
Z iota. Z root minus 1.
I don't remember, but I remember we checked the units for the ZI for the
Yeah,
Gaussian integers.
so it is a good exercise for you. Do it on home and let me know. I guess it is 2 statement, but I'm forgetting this time. Like, see, I learned this thing long ago. So let me write a statement here. So check this. I'm claiming something. Claim units of Z root minus 5 is equals to A plus b root minus 5 such that a square plus 5b square is equals to 1. These are the only units. Like in z iota, you can see there are only 4 units. A square plus b square equals to 1. So only 4 possibility you can see. 1 minus 1 iota minus iota. These are only 4 units you can see.
Yeah.
In this way you can conclude. So this one is a exercise. So not I am not to clean exercise. Check this. Check this. So now, as Muthukumar pointed out that 2 divides 6, which is same as 1 plus root minus 5 into 1 minus root minus 5, but 2 does not divide any of this. And so this implies 2 is not prime. But after doing above exercise, you can see all the units in this ring and you can claim that 2, but do above exercise and then after conclude that 2 is irreducible element. So this will give you an example of a ring where you can find a prime element, sorry, a irreducible element which is not a prime element. So this is the example. Okay. I hope you will do this more rigorous and okay. This is fine, right? Damas, is this fine?
Yeah, it's fine.
Okay, try to do this in exercises. I hope this is done in your class. That's why I'm not doing much rigorously this because this is a standard kind of fact and this should be done in class, right? Okay, so next one is if R is an integral domain, then any irreducible element in R is prime. R is an integral domain. R is an integral domain, then any irreducible element in R is prime. Element in R is prime. Is this true or false? Damas, is this true or false? Vaishnavi, I gave you above a counter example.
Yeah, this is general false.
Yeah, false by above justification. False by above example. We gave an irreducible element which is not a primary. Third part. If R is a PID, then any two elements of R have a greatest common divisor. C. Sorry, what is this C? Yeah. If R PID, then any two element of R have a greatest common divisor. Greatest common divisor. Okay. So do you know this fact that if like in general ring the GCD may not exist? Do you know this fact?
Sorry, can you repeat? Just say.
In general ring R, the GCD may not exist. Greatest common divisor may not exist. Do you know what is GCD?
The greatest, yeah.
Yeah.
We
How
know.
we define this? Do you know? Suppose you are given the two elements A, comma B in R. How you define GCD of two elements in B? You know this or not? Tell me. Okay. How you will define GCD of A, comma B?
Yeah.
In
Yeah, I
any
think
ring R?
we need to find like other elements like
Yeah.
X
Is
and
an
Y such
element
that.
GCD of an element A, comma B is an element B in R such that
Yeah.
D divides A and
Yeah.
D divides B.
Sure.
Yeah, it should be greatest. If
Yeah.
E belongs to R such that E divides A and E divides B, this should imply that E should divide D also. D should be greatest among all divisors, right?
Yeah.
Yeah. So this is the definition. So I am saying that in general ring, the GCD may not exist.
Mm.
Can you see this? Think about this ring Z root minus 5. Search here for two elements for which you cannot say GCD. I gave you already an example, right? This see this kind of factorization 6 equals to 2.3. Then what you can say? Like you 2 divides 6 and 1 plus root minus 5 divides 6, then you can say something like what are choices of A, B, D, and E? You should get this thing. Can you see this or not?
Yeah, okay. You are saying from that example,
Yeah.
whereby we have seen that the 2 divide 6,
Yeah.
but the 2 doesn't divide the product of these.
Yeah.
1 minus root minus and 1 plus root minus.
Yeah. So what are two numbers A and B such that their GCD does not exist?
The A should be 6 and the B should be the product of the roots.
Hmm? A should be 6 and what B?
I'm saying the B maybe should be the product of 1 plus minus root.
Suppose
I mean,
take B. Suppose take B equals to 2. Then what?
If we take B is equal to 2,
Huh.
and A is 6.
Yeah. Then what?
Yeah.
What
the
is
D will be 2.
D would be 2. Now say E equals to 1 plus root minus 5. Then what? E should divide A and E should divide B.
Yeah.
But E divide 2. 1 plus root minus 5 divide 2.
No, it doesn't.
Yeah. So how you will claim 2 is GCD?
Yeah, it is not.
Yeah. So that is the problem. Agreed or not?
Yeah. Yeah, it is
So
not.
there is the problem comes arise in picture. So there neither 1 plus root minus 5 divide 2 or neither 2 divides 1 plus root minus 5. You cannot hold this second property. So there does not exist GCD in that for in these two elements, right?
Yeah.
Yeah. So this is the argument. So so that's what I want to say. GCD does not exist in general. So, but this option says that if R is a principal ideal domain, then any two element of R is a R of R is GCD. What I write? What is the statement?
The PID. If R is a PID,
Any
then
two have a greatest common divisor. Okay, fine.
yeah.
Yeah. So suppose take two elements. Now prove this statement, right? For PID, this is true statement. So let's prove this. How will prove? Suppose you take any two elements A and B. You have to claim that their GCD and they have a greatest common divisor.
Yeah.
So, like let A comma
B.
in R. Then take I is equals to ideal generated by A and B.
Yeah.
And claim that let into element. Okay. Okay. So now since it is a principal ideal, so it should be generated by some element, right? It should be some element D. D belongs to R. Like it should be principal, right? Agreed or not?
Yeah.
It should be
Because
principal, right?
because it is principal. Yeah.
Yeah, it
It
should
should
be. It
be
is a
generated
principal
by
ideal
one.
domain, so it should be principal ideal, right?
Yeah.
Yeah. So it should be principal. So A, that means ideal generated by A is contained in ideal generated by B, right? Contained on equals, right?
Yeah.
This means A belongs to ideal generated by D, right? Agreed or not?
Yeah. Yeah. Yeah.
So that means A is equals to dx for some x in R, right?
Yeah.
That means D divides A, right?
Yeah. Okay.
Okay.
So similar for B.
Similarly, D divides B, right?
Yeah.
Now I am claiming that this D is a GCD. Can you see my argument? How I am proceeding? Like I claim that it should be some principal ideal, and now I am claiming that this principal ideal generator is the GCD, right? So claim GCD A comma B is D. So how you will claim prove this claim? The first condition I already proved, like if D is a GCD, then D divides A and D divides B. That I already
So I
showed,
think
right?
so. I think is the consequence directed by the definition.
Yeah.
That since the D divides A, D divides B. So
yeah, but we have to show another condition, right? If E divides A and E divides B, right?
Yeah.
This one remain to show, right?
Yeah.
Then to show E divides D also, right? So E divides A means what is the meaning of E divides A?
A is the multiple of E.
A is the multiple of E, right? A is
Yeah.
equals to E times something alpha, and B is equals to E times beta. So that means A belongs to ideal generated by E and B belongs to ideal generated by E. This means A is ideal generated by A comma B is contained in ideal generated by E, right?
Yeah.
But ideal generated by A comma B is same as ideal generated by B, right? D, right? Right?
Yeah. Yeah.
So that means
By
ideal generated by D is contained in E, right?
yes.
So that means D belongs to ideal generated by E, right?
Yeah. So D
So
is
that
equal
means
to
what?
D is equal to E a multiple of E.
Yeah, D is equals to E A, right?
Yeah.
So that means what?
E divides D.
E divides D. So we are done, right?
Yeah.
So done. So what we have done? We have proved that if R is a PID, then GCD exists. Then two element of R has a GCD, greatest common divisor. True, right? Agreed or not? Is this proof or clear
Yeah.
or not?
Yeah, it's clear for me. It's clear.
Let me ask Muthu Kumar. Muthukumar, is this proof clear or not?
It is clear,
Okay.
but in the class they have given a different proof using associates.
Okay, you can use that also, but this proof seems to me more better than using this
It's
kind of-
okay.
Yeah, fine. Okay, the next statement is that if R is a PID which is not filled, the maximal ideals of R are generated by irreducible elements. If R is a PID, which is not filled, the maximal ideals of R generated by irreducible elements. Okay, is this true or false? Tell me, if R is a PID which is not filled, in PID every prime element is irreducible element, the maximal ideal of R are generated by irreducible element. I gave you definition of a irreducible element. So how you will prove this? Is this true or false? Suppose M is a maximal ideal. So since it is a PID, it should be generated by some single element, right? So now you are claiming that this generator is an irreducible element. Suppose not, then what happened? Okay, let me write. Not the maximal of R. Let M be maximal ideal of R. This implies M is equals to generated by some element D. To show, we have to show D is irreducible. D is irreducible, we have to show, right?
Yeah.
So for irreducible, what we have to do, like if D is equals to BC, then
Either B is a unit or C.
either B unit or C unit, right?
Yeah.
Or C is unit. So how we'll prove this? We have to show D is irreducible element. We are in a PID, right? So how we'll prove
Yeah.
this? This is almost easy, right? How we will do this? Tell me. If B is a unit, then we are done. If B not unit, then what? If B unit, then we are done. It is irreducible
Yeah.
element.
Yeah.
If B is not unit, done. If B is not unit, then what? You have to say something, right?
Yeah.
What is the if B is not unit, then we are saying that this, as in, I'm claiming that this ideal generated by D is contained in ideal generated by B. Agreed or not?
Yeah.
But
Yeah. So the
this-
D is not maximum.
yeah, that means it is not maximal ideal.
Yeah.
Not maximal. So this implies that B must be unit, right?
Yeah.
So this implies that D is irreducible. Agreed or not?
Yeah. I agree.
D is irreducible element. So we have proved that in a PID, the maximal ideals are generated by irreducible element which are same as a primary. E. If every ideal of R is principal, then R is a PID. Tell me, is this true or false? Muthukumar, is this true or false? Muthukumar is not there. Vaishnavi, is this true or false? I guess you are tired now. This is 2-hour session. Too much. It's too much. Vaishnavi, are you in class or not?
Yeah, yes, sir.
Yeah.
So tell me, is this true or not?
No, R must be an integral domain also.
Okay. So give me an example where it is not true. Give me a ring which is in which every ideal is a principal ideal, but it is not an integral domain. Otherwise, prove this statement is a true statement.
Z mod 4 is it?
Okay, you are giving right example. Yeah, I am also thinking about this example. Z mod 4Z. So what are ideals in this ring?
It's 0, 1.
Okay. Zero ideal is first ideal. And what are other ideals?
1.
Ideal generated by unit ideal, which is same as R. But other than this, if an ideal contains 3, then it contains whole of 3 because 3 is also unique. So the only possibility remains is 0, I, which is same as ideal generated by 2. So you
is
can
it not the definition of principal ideal domain?
no principal
Every-
ideal domains also requires integral domain, right? But this is not integral domain. Every ideal of R is principally just same. So I gave you example like Z mod 4Z. Every ideal is a principal, but it is not an integral domain, hence not a principal ideal domain, right? Agreed or not?
Okay, because we have defined for this only by assuming R is an integral domain.
Right. R should be integral domain. So this is
Okay.
the counter example. Agreed or not? Muthukumar, do you agree with this or not?
Okay.
Okay. Damas, is this clear or not?
Yeah, it is clear.
Okay, fine. So last part. So what is the last part? If R is an integral domain and A is an irreducible element of R, then the ideal generated by A is maximal element. Ideal generated by A is maximal ideal. Tell me, is this true or false? If R is an integral domain, and A is an irreducible element of R, or then the ideal generated by A is maximal element. Is this true or false? Now you are not in a PID. Is this true or false? In PID, you use the argument the ideal should be principal. See, take the ring R is equals to ZX, right? It is an
Yeah.
integral domain since Z is an integral domain. So A is an irreducible element, 2 is an irreducible element. So ideal generated by 2 is not maximal, it is contained in ideal generated by 2, x, right?
Yeah.
So it is not maximal. So this statement is a false statement, right? Agreed or not? Above, I gave you a proof for an principal ideal domain which every irreducible element generates maximal ideal. But here I gave you a counter example for an integral domain case where the ideal generated by irreducible element is not a a maximal ideal.
Mm.
Is this clear? Damas, is this clear or not?
Yeah, it is clear. Yeah, since we said 2 is maximum and
Yeah.
but we have another containment, the 12
Yeah.
index.
Yeah. Muthukumar, is this clear or not?
It's clear.
Okay. Fine. So we have now only 2 minutes remaining. So only one problem remaining. So we will do this in next time. So because now we have only 2 minutes. So if you have any suggestion or comment you want to make, or you can ask something, you can do that thing, right? Any suggestions? Any comments? Okay. So shall I stop this session here, or you want to say something?
For me, it's actually just thanks and appreciation for the session.
Thank you. Thank you
Yeah,
for
and,
joining
for
and
your-
participating in this session. So try to make this more interactive because I just want to interact with you and solve the exercises. Otherwise, you can solve this in your homework.
Yeah. Thank you so much, sir. It's a great help.
Yeah, I guess you enjoy. I hope you enjoyed this session and like you will.
Yeah, very much. Very
Yeah.
much.
Okay, thank you. And you want to say something, or you have any doubt?
I know it's okay.
Okay, thank you. So we